Okay, the final talk of the session before lunch is Ben Tofflemire on accretion dynamics in pre-main sequence binary systems.
Yes. All right, can you all hear me? Yes, okay.
You good?
Yes. Okay, all right, well, thanks for the introduction, and thank you to the organizers for giving me the chance to share some of this work today. As the session would suggest, we're interested in stars and their environments, and I'm interested in how environments shape stars. So particularly, I'm interested in how binarity affects the interaction between pre-main sequence stars and their circumstellar disks. And the motivation for this project has come from this growing body of evidence that suggests that this star-disk interaction is going to play an important role in the formation and evolution of low-mass stars, and in the acknowledgement that binaries have the ability to fundamentally alter this interaction. So I'm going to start just briefly with single stars, where we have this really well-established model, this magnetospheric accretion paradigm that we assume single stars go through. And it's nice because it gives us a way to understand the joint evolution of a star with its disk through this phase of star formation. And so, with this model, we can say, we have these important things that happen, like the star can continue to gain mass, a significant a non-negligible portion of its final mass. We also have a way to regulate the star's angular momentum through this disk locking mechanism, which can slow the star's rotation as its stellar magnetic field threads this slowly rotating disk material. And then, of course, the disk is going to be affected by the way the star and the disk interact. So we kind of have this model to understand how disks are going to evolve, give us an idea for their timescales, their stability, their irradiation, which are, of course, all important ingredients for planet formation. So while all of these are certainly far from being solved problems, they at least exist within this framework that we have for single stars to understand how these systems are going to evolve. But of course, we know that binaries are a common outcome of star formation, and we can't necessarily assume that all of these processes are going to hold in the binary environment. Now, the way that a binary is going to diverge from single stars is going to depend heavily on the binary orbital parameters. So that's obviously a huge parameter space for us to talk about. So today I'm just going to focus our discussion to close binaries, and by close I mean with respect to the size of a protoplanetary disk, so let's say less than 50 AU, and binaries that have non-zero eccentricity, so things that are not circular. So under those conditions, we have some predictions for how this binary disk interaction is going to take place. So to give you an idea of how that is going to happen, I have a simulation here from Diego Munoz for an equal mass binary with an eccentricity of 0.5. And the color scheme I'm showing you here is the logarithmic surface density, spanning about 5 orders of magnitude from low densities in black to high densities in white. And so as these stars go through their orbit, you have this very kind of dynamic interaction where orbital resonances are going to clear out this central region, the central cavity around the stars, giving rise to this circumbinary disk. And then you'll also notice that at every apastron passage right there, where the stars are furthest from each other, that you have this interaction with the circumbinary disk. It creates these streams of material that drags them across the cleared gap, fuels these small circumstellar disks, and gives rise to bursts of accretion near periastron. So if we look at the mass accretion rate as a function of orbital cycle that comes out of this simulation, you'll see that we find these, or we should expect to find bursts of accretion during every orbital period that can increase the instantaneous mass accretion rate by a factor of 10, and that these events should occur preferentially near periastron passage. So if this is indeed the way in which binaries are interacting with their disk material, we have a very different scenario than in single stars. We have this gapped disk architecture. The binary is potentially dynamically heating the circumbinary disk. This also gives rise to this variable accretion behavior that is periodic and leads to these pulsed events. And the degree to which disk locking and angular momentum regulation will take place under this, or in this scenario is also pretty poorly understood and could potentially be less efficient. I think it's also worth noting that basically every eclipsing binary that we have falls within this regime and has potentially experienced this stage of star formation in a very different way than in a single star. Okay, so the way in which we want to go about trying to test these predictions is to find some young binaries and look for pulse accretion events. So the two binaries that we have gone after are DQ tau and TWA3A. Both are short period, both are highly eccentric, and have near equal mass, have a mass ratio near unity. Both also have spatially resolved circumbinary disks and evidence for ongoing accretion. So the way in which we've done this is with a monitoring campaign at the Las Crumbas observatories. We've observed each binary for 10 orbits at a cadence of 20 observations per orbit in this suite of filters up there. And then in the case of TWA3A, we also have time series SALT spectroscopy that overlaps with our photometry. So I want to focus mostly on the spectroscopy today because that's the newest stuff and the stuff that I'm most excited about. But just to briefly talk about the results from our photometry, I'm plotting here the mass accretion rate that we observe derived from the U-band as a function of orbital phase. And so you can see that just as models would predict, we have these consistent bursts of accretion that occur near periasteron passage, which drives pretty well with the models, which I'm going to show here now in red. So the fact that these agree anywhere as near as well as they do is amazing to me. And if you want to ask me why there's differences, I'd be happy to talk about that in the questions. But let's just take these simulations at face value and say that they're capturing the important physics that we need to describe these systems. Okay, but moving on to the spectroscopy. In the top panel here, I have our full U-band observations for TWA3A. In the lower panel, I have a subset of those data where each vertical blue band marks an epoch where we have spectroscopy. And these vertical dashed lines are periasteron passage. So we have pretty good phase coverage over about 3 orbital periods. And the thing that I'm most excited to do with these data is to compare not only when accretion is happening, which the photometry can tell us, but to tell us where the accretion is happening. So to do that, we're going to use this helium-1 accretion tracing emission line, 5876. And so I'm showing you 3 subsets of spectra here. The ones at the bottom are just after periasteron, so that's when the accretion rate is high. We have one in the middle, which is near apasteron, when the accretion rate is low, and then 3 at the top where, again, the accretion rate is high just prior to periasteron. Associated with each spectrum, we also have, let's see if I can get this to go. We also have a red and blue line dash here. So the blue line marks the primary's velocity, and that's going to cross over here, and the red line marks the secondary velocity. So in addition to tracing accretion, this line also has a chromospheric component. We're working to remove that component now, and so that's a little bit still in the works, but we are, have a crude step that we've done so far, and you can see that during high accretion rate observations, our line becomes broader, it becomes stronger, consistent with the photometry that we observe, but the velocity at which that emission is coming from is very consistent with the primary's velocity. And so what we think that's telling us is that these streams that are coming in from the circumbinary disk are preferentially falling onto the primary star. Okay, so in addition to just being a cool measurement that we can make, I think this is a really important constraint on numerical simulations, because more than just being cool, it's also not what most simulations would predict. So a vast majority, almost everyone you can find in the literature, would suggest that the secondary, not the primary, is the dominant source, should be the dominant receiver of an accretion flow. So we don't find that. The only viable model that we've been able to find that suggests the primary could be the dominant accretor are the ones that I showed you earlier from Diego Munoz. And the way in which the primary is the dominant accretor is that the disk, the inner edge of the disk itself, is eccentric. And so as the stars go through their orbit, one star here passes closer to the inner edge of the circumbinary disk than the other star. So during each orbit, this star induces a larger stream, which you can also see here, and accretes more material. This eccentricity precesses, though, over many hundreds of orbital periods, and then at a later time, the secondary could be the dominant accretor. So the reason that these simulations resolve this behavior and others don't is that these run for many thousands of orbital periods. The circumbinary disk reaches a stage of relaxation that others don't, and you can begin to see these secular interactions between the binary and the orbital, between the binary orbit and the disk material. This is something we're excited about, and certainly will help us motivate future observations to look for this flipping in the future. So just to summarize, we find these bursts of accretion near periastron that are very similar to what simulations would predict. And with the spectra, we can begin to find where this accretion is happening and really start to constrain these models for binary accretion. And so I think we're kind of moving towards a point where we can say, these are how binaries are different, and potentially this is why, or potentially these are some important things to consider when we think about comparing them to single stars. So I'll go ahead and stop there and take any questions.
Thank you. Okay, we are on schedule. Question here first, and back there second. Raise your hand again so she can see. Thank you.
Chris Tinney, UNSW Sydney. So in addition to looking at the emission line spectroscopy, are you able to use your spectra to look for absorption lines from the accreting material when it's not actually accreting to better understand the structure?
Yes, that's kind of was the main motivation for getting the spectroscopy. And so that's been difficult. We haven't found anything conclusive. There are some interesting kind of consistent absorption features in the H-alpha profile that we're still looking into. But kind of knowing what temperature that material is going to be when it comes in and what signatures to look for has been hard to try and nail down, and nothing obvious is popping out right now. But thanks for the question, yeah.
A question over there.
Marina Kunkel, Western Washington University. So there are two scenarios in which binary stars seem to form in simulations, that either from the collapse of the disk or collapse of a protostellar core. Do you have some thoughts about how these two different scenarios could influence what you're observing? Yeah,
absolutely. So I think for what we're observing here, I would lean towards these being formed by a disk fragmentation scenario. Just because if you're going to form binaries dynamically, you can certainly get them as close as the binaries that I'm presenting here. But depending on the timescale in which that interaction takes place, I'm not sure that the disk material would be maintained in the same way. Like you could form a binary dynamically and destroy all of the surrounding disk material and leave you with a really short lifetime or very little disk material. I wouldn't claim that all short binaries go through this path, but I think these ones are, well, it's hard to say what fraction, but I would say that these are coming from a disk fragmentation scenario.
Other questions in the back?
Hi, I'm Nicole Arulanantham from the University of Colorado Boulder. So it seems like you focused here on systems with equal mass components. And as someone who's interested in maybe enhanced accretion due to star-planet interactions, I was just wondering if you have a sense, either observationally or from simulations, of how small you can make that mass ratio between the two components and still see this kind of phased accretion.
Yeah, so I can't really comment on it from an observational standpoint, but I can't remember his first name. His last name is Miranda. He's a collaborator of Diego Munoz and Dong Lai. And they've done these simulations for a variety of mass ratios, kind of at a less spatially resolved regime. And I think if you go down to mass ratios of roughly 0.2, the same behavior will apply. If you go below that, I think there's a different area of simulators who are more interested in the kind of the planet star interaction. And in that case, you kind of, I think the root of the difference is that you're not clearing out this cavity in the same way that you do with two stars. And so you have material both interior to the planet and exterior to it. So you kind of have a different different scenario there.
Thank you. Any other questions or comment? No comment. Any other questions or questions? There's a question. Yes, I feel certain it's a question and not a comment.
Nice talk, Kevin Covey, Western Washington. Related to that, I guess, does the accretion onto the primary, do you expect that could actually significantly alter the mass ratio if that were happening for a very long time?
Yeah, that's a good question. So I guess I would just back up to say that a lot of people that do these types of simulations assume that the secondary will always accrete more, and that will act to make the mass ratio unity. And especially people that do like gravitational waves and binary black hole mergers care a lot about this. So I think at this phase of star formation, the disk mass is so low, the accretion rates are so low that I don't think we're in an area where we're going to see significant changes throughout the rest of this disk variant lifetime. But for if this is still holding, the fact that you could have it switch back and forth and the amount of material accreted onto one star or the other is relatively even. At least from these models, I wouldn't expect mass ratios to change significantly based on what we're finding.
Okay, let's thank our speaker again.